So let's take an example. Let's talk about a first order system, and I'm going to apply an unit step input, and I'm interested in how it responds. There's my transfer function, standard form first order, just for this example. So the output must be equal to that, which is an unit step 1 upon s multiplied by that first order transfer function, and I get this thing, which isn't necessarily that helpful just yet. So but that's the answer. Okay. When I ask what is the output of that system, there it is. That is a description of what the system does. Trouble is, it's not really very helpful like that, because it's still in the Laplace domain. What I'd like to do is to convert it back, but there's a snag. Okay. That is not listed. I think I've got them here. That is a copy of the Laplace transform set from the Bird and May books that you sometimes get in exams. You know the ones I mean? Yeah, those booklets. And that's just copied from there. So if I want to find this shaped function in my transform tables, I've got a slight problem because it's not there. So what am I going to do? We can split it into. Can we split it into pieces, the end result of which is that each of the pieces does appear in the tables, so we can convert it back? So I'm going to take this expression and see if I can split it to start with into something over s plus something over s plus a, because, I hope at least, I've got something over s just up here and something over s plus a just there. So I need to split this thing up that way. So what techniques have you got in your mathematics armory to split that up? Bear in mind, when I say split up, just writing them apart from each other and saying times doesn't count. Okay? I need to split these up into a sum of components, not a product. I need to be something plus something else, not something times something else. So what techniques have you got? Partial fractions. So we need to apply partial fraction expansion to these expressions to split them up into a shape that is available in there. Are there other methods? Yes. Go and find a book with a more extensive set of transforms. Okay, because no two information books will have the same table. They'll be different. But that only works so far, because you've got to do this in an exam and you're just given the set of tables. So it's probably wise to learn to use that one, which is, I think, already on the Blackboard site under data. Get used to the one that you're going to see in the exam. It's actually got more on than this page I'm showing you. So this is, goodness knows what's happened to these animations. So that's my expression, top right. I want to split it into pieces that do appear in my tables, so I need to do some partial fractions. I've got to ask you this question. Who remembers how to do partial fractions? Nobody. Who kind of remembers how to do partial fractions? A few of you. And who's completely forgotten how to do partial fractions? Many of you. Okay, that's not unusual. For these sorts of questions, you do need to drag that knowledge back up to the top. Okay, and it's probably a long time since you've expanded using partial fractions. And I also know that in this room there will be at least 2, possibly 3 different techniques for doing so. Okay. Some people do it by comparing coefficients, some people do it by using the cover-up rule, we've all got a different way of expanding partial fractions. You do need to remember how to do that. I do it by comparing coefficients, so I'll just very quickly run through this example so you can see what's going on. I've generalized my expression a over s plus a, and I want to split it up into something over s plus a. So the supposition is that if I want to make these two things equal, I can multiply this back out again, so the two things have got the same denominator, and that means that a must be a1 times s plus a2 times s. Okay, just multiplying out the sum, the right hand side, the sum of components, to give me an equivalent numerator on those fractions. I then just compare coefficients. Okay. And if I look at the numbers terms, well, on the left hand side is a, on the right hand side it's a1 times a, so that gives me a value for that coefficient. I look at the s terms, there's none on the left hand side, it's a1 plus a2 on the right hand side, so I get to evaluate a2. So that's a1, that's a2, and now I'm in a position to do a transform. So a over a times 1 upon s, back to the tables, that simply comes out as a upon capital A upon lowercase a, minus a upon a times this term 1 over s plus a. Well, that comes out as a over a, this is the amplitude number. The 1 over s plus a gives me e to the minus at. Okay. Go through it yourself, start to wake up those partial fraction techniques and get to grips with the Laplace transform tables. I go back to the tables. Oops. The terms we've used are, this is k upon s. I had big A upon little a times upon s, so that simply becomes big A over little a. And the other term was this one, 1 over s. They've actually got s minus a in these tables. I had big A over little a over s plus a, so this becomes big A over little a e to the minus at. So big A over little a times 1 minus e to the minus at. Okay, so this is a size thing, isn't it? A upon a here just tells me how big this output is going to be. If that happens to work out as 100, then the output is going to be about 100 times bigger than the input. The part in the bracket, which is the time function, tells me about the shape or the dynamic of the response. So let's forget about size for now and just look at this function here. Let's do it from that page. 1 minus e to the minus at. What does that look like if I draw it on the graph with time on the horizontal axis? What shape is it? Okay. 1 minus e to the at. When time is small, when t is 0, what happens to e to the minus 0? That's naught, isn't it? That's 0. So what I get is 1. So I start out 1 minus 1 equals 0. So I begin at 0, which kind of makes sense. What happens when t is very large? Then this becomes minus a very large number. So that becomes 0. E to the minus a very large number becomes 0, doesn't it? So this becomes 1 minus 0, which is 1. So I start off with a value of about 0, and I end up with a value of about 1. In between, is where a number of you have been drawing shapes, and that's quite right. What we need to do is to understand the shape of this exponential as we travel from 0 to 1. This is just putting the actual numbers that we used in the example back in. So let's try it at different values. What I've done here is we had 1 minus e to the at. Okay, and this is 1 minus t upon tau. You'll see the relevance in a minute. At time equals 0, the output equals 0. We did that one. When time gets larger and larger, the output is approaching 1, it's approaching 100%. What happens in the bits in between? Well, when time is equal to tau, this becomes 1 minus e to the minus 1. Anybody know how big e is? Yeah, it's 2 point something, isn't it? So 1 minus 2 to the minus 1, well, if it was 2, that would be a half, wouldn't it? So it's about a half. If I make t twice as big as tau, this becomes 1 minus e to the minus 2. Make it 3 times tau, e to the minus 3, and you can see it's getting smaller, but it's getting smaller in smaller steps. So the difference between 0 and 1 tau actually works out at 63%, and after that it gets less and less of a change. So it's exponential that some of you described, but what it does is it stays up there. It doesn't come back down again. Okay, it's an exponential which is steepest at its beginning, and it levels off and it settles to a steady state value, in this case of 1. Have I got a picture? There it is. The red line is my unit step input, and the blue line is my first order system response to that input. After, in this case, this has been normalized after 1 time constant, I get to 63% of the final value. After 3 time constants, I get to 95% of the final value. 1 minus e to the minus t upon tau. If we've got a size number in front of it, the whole thing just gets bigger, but it stays the same shape. The dynamic is the same. What's the point of standard forms? The point of a standard form is that once you've identified something to be a first order system and you've manipulated it into the standard form, they all behave exactly the same. They all do this. If it's a first order system, it will respond to an unit step like this, no exceptions. And that's why we like the standard forms. That means I only have to remember one equation. I don't have to keep working it out. Is that okay? Yeah, partial fractions, Laplace transform tables, and a bit of algebra, and we've got a time response for any of, or all I should say, of our first order systems. Okay, so what's a first order system do? If I put in an unit step, it responds like that. What does it mean? Well, this number on the time axis is tau. Do you remember where tau came in when we were developing our standard form? Oh well, that's defective. Let's not worry about writing on there. Do you remember where tau came from? What name had we given tau?
Time constant.
The time constant. After one time constant, this output reaches 63% of its final value. Its final value in this case is 1. After 3 time constants, it reaches a final value of 95%. Sorry, it reaches 95% of its final value. How long does it take to get to its final value? This is the equation describing that graph. How long does it take to reach its final value? Never, thank you. You guys have studied maths for years, you should recognise that if you look at this kind of exponential, it never quite gets there. It becomes asymptotic, but it never actually reaches the final value. So, if I'm an engineer and I'm concerned with the dynamic performance of my system, and my boss asks me, oh, how long does it take to get there? And I say, never does. Because that's what the maths tells me. And it's true. So, if this first order response is describing, I don't know, a heating process or a position control process, that question is quite difficult to answer. How long does it take to get there? Forever. It never gets there. That's the mathematically precise answer. So we need to think of other ways of defining what this graph is telling us. We need to come up with some words to describe it. It reaches 95% of the final value after 3 time constants. So the time constant's got to be small for a fast response. Oh yeah, I'll introduce the word lag here. Okay. This system is known as a first order lag. And the reason for that is because the S terms are in the denominator. Okay. Most real systems exhibit lag behavior. Not everything, but most real systems do. Because generally speaking, the output from a system happens after the input's been applied, not before. We tend to turn that sort of thing on its head when we're looking at repetitive inputs like sinusoids. Okay, so I've got a system that never gets there, but I do know it reaches 95% of its final value after 3 time constants. I'm going to pick on that number in a bit, I think. I'm going to define an engineering it's close enough sort of definition to get away from the maths saying it never gets there.